January 1913, Highland Park, Michigan. In a freezing third-floor design room, three Hungarian immigrants huddle around a blackboard, scratching calculations that would horrify every established automaker in America. European engineers had spent decades perfecting precision, complex engines with 47 different parts, machined to thousandths of an inch, requiring specialized tools to repair. The automotive elite believed this was the only path to quality, but Henry Ford was asking his team to do the impossible: build an engine using principles that seemed barbaric, wide tolerances, simple parts, materials so basic that farmers could repair them with hand tools in a cornfield. Every expert predicted failure. Yet somehow, these crude 1913 Model T engines would run 500,000 miles, while today's sophisticated cars die at 150,000. The question isn't how Ford succeeded, it's how we lost the secret. The calculations on Joseph Galam's blackboard told a story that defied every principle of automotive engineering: a 177 cubic inch, four-cylinder engine that must survive conditions no European luxury car had ever encountered. Eugene Farkas traced stress distribution patterns with chalk-stained fingers, while Charles Ballou calculated thermal expansion rates for materials that American foundries had never attempted to cast. Ford stopped pacing and jabbed his finger at a specific line of mathematics. "Show me again how we get 500,000 miles from parts a farmer can file by hand." His voice carried the edge of a man who had staked his reputation on an engineering philosophy that sounded like madness to trained professionals. Galam wiped condensation from his wire-rimmed spectacles and pointed to a cross-sectional drawing of the proposed engine block. "Single casting, Mr. Ford. 4 cylinders and crankcase in one piece. Vanadium steel throughout." His Hungarian accent thickened when he concentrated on technical details. "Compression ratio 4.5 to 1. Side valve design. Thermosiphon cooling." Every specification violated established automotive wisdom. Cadillac's latest engine required 47 precision-machined components, each built to tolerances measured in thousandths of an inch. European manufacturers like Mercedes built engines with overhead camshafts, multiple carburetors, and bronze fittings that demanded specialized tools and trained mechanics. Their vehicles served wealthy customers who maintained private garages staffed with professional technicians. Ford's target customer owned no garage, employed no mechanic, and needed transportation that survived Nebraska blizzards and Texas heat waves with minimal maintenance. The average American farm sat 20 miles from the nearest town, 40 miles from a trained mechanic. When a Ford engine failed, it had to be repairable by a blacksmith using basic hand tools, or it was worthless. The numbers painted a devastating picture of the challenge they faced. In 1913, the average automobile cost $1,800, equivalent to 3 years of wages for a factory worker. Ford had already cut the Model T's price to $600, but even that remained beyond reach for most Americans. To achieve his ultimate goal of a $500 car, Ford needed to slash manufacturing costs by another 20% while maintaining the durability that made farmers trust the Ford brand. Meanwhile, European manufacturers dismissed American automotive efforts as colonial vulgarity. A recent British automotive journal had declared that mass production may suit frontier markets, but European customers demand individual craftsmanship. German engineer Wilhelm Maybach, designer of the prestigious Mercedes Puy, had visited Highland Park the previous month and pronounced Ford's methods industrialized barbarism. The criticism stung because it contained elements of truth. Model T engines were noisier than European equivalents, rougher in operation, less refined in every measurable way. But they possessed something European luxury engines lacked: the ability to function under conditions that would destroy delicate, precision machinery. Farkas pulled out a folder of field reports from Model T owners across the American heartland. A Nebraska farmer reported 50,000 miles with routine maintenance consisting of occasional oil changes and spark plug cleaning. A Texas rancher used his Model T to power a threshing machine, lumber saw, and water pump, applications that would annihilate conventional automobiles. Most significantly, Farmers were buying second and third Model Ts not because their first vehicles had failed, but because Ford's proven durability made them confident in the brand. The engineering challenge extended far beyond mere durability. Ford's Highland Park plant currently produced one Model T every 3 hours, operating 24 hours daily, 7 days weekly. But orders flooded in faster than production could match, 15,000 in the first 5 days after the latest price reduction. Each engine required 14 hours of hand assembly by skilled workers, creating an insurmountable bottleneck that prevented Ford from achieving true mass production. Charles Nash, president of General Motors, had captured the industry establishment's sentiment perfectly. Ford is trying to build farm equipment and call it an automobile. The accusation carried weight because Ford's specifications seemed to confirm it. Wide tolerances that allowed field repairs also created engine noise and vibration. Simple side valve designs eliminated complex valve adjustments but reduced power output. Thermosiphon cooling systems had no pumps to fail, but they also limited engine performance in extreme conditions. Ballou spread metallurgy reports across a wooden table, his breath visible in the unheated design room. "The answer is here," he said, tapping a technical analysis of steel samples recovered from a crashed French racing car. Vanadium steel, tensile strength 170,000 pounds per square inch. 3 times stronger than conventional American steel. Ford leaned over the reports, studying chemical composition charts that showed vanadium steel's superior resistance to fatigue, impact, and thermal stress. European racing teams had discovered that vanadium steel components could withstand punishment that shattered conventional materials. But American foundries had never attempted to cast vanadium steel in the complex shapes required for automotive engines. The metallurgy breakthrough offered a solution to Ford's central paradox, building engines simultaneously crude enough for field repair, yet durable enough to survive 500,000 miles of abuse. Vanadium steel's exceptional strength would compensate for wide manufacturing tolerances, creating robust components that farmers could service with basic tools while maintaining structural integrity far beyond conventional materials. But implementing vanadium steel casting would require revolutionary changes to Highland Park's production methods. New furnaces, modified molds, retrained workers, and manufacturing processes that had never been attempted on an industrial scale. The investment would consume Ford's entire cash reserves and leave the company vulnerable if the experiments failed. As winter daylight faded through ice-covered windows, Ford faced the choice that would define American automotive manufacturing for the next century. He could abandon his 500,000-mile engine dream and follow established European methods of handcrafted precision. Or he could bet his entire company on an untested combination of metallurgical science and manufacturing revolution that promised to democratize automobile ownership if it didn't destroy Ford Motor Company first. The Highland Park foundry glowed orange against the February dawn as molten vanadium steel reached 2,800 degrees Fahrenheit in the massive crucible. Joseph Gaylam adjusted his leather apron and signaled the pourers, watching as liquid metal flowed into a sand mold that would either vindicate Ford's revolutionary vision or consume his remaining capital in a cascade of molten failure. The mold itself represented a radical departure from established automotive manufacturing. Every other engine manufacturer in America built power plants by machining separate cylinders and bolting them to separate crankcases, slicing sorping, a time-tested method that allowed precise quality control and easy replacement of individual components. Ford's engineers had designed something unprecedented: 4 cylinders, intake manifold, and crankcase cast as a single monolithic block. The technical challenges were staggering. Vanadium steel contracted differently than conventional iron as it cooled, creating internal stresses that could crack the casting. The complex internal passages for oil circulation and coolant flow had to be formed by sand cores that might shift during pouring, creating unusable blocks. Most critically, the entire casting had to maintain dimensional accuracy across a component weighing 180 pounds, 30 pounds lighter than equivalent multi-piece designs, but infinitely more difficult to manufacture successfully. Steam hissed as cooling water contacted the mold's exterior surface, beginning a 12-hour cooling process that would determine whether months of metallurgical research had produced a breakthrough or an expensive lesson in the limits of industrial ambition. Gallum made notations in his engineering logbook, recording poor temperature, ambient conditions, and cooling rates that would guide future production runs. The engine specifications emerging from Ford's design process horrified European-trained engineers who visited Highland Park. The compression ratio of 4.5 to 1 seemed absurdly low compared to the 6 to 1 ratios found in premium European automobiles. The side valve flathead design placed both intake and exhaust valves beside the cylinders rather than overhead, eliminating the complex valve trains that European manufacturers considered essential for performance. Thermosiphon cooling relied on natural convection rather than mechanical water pumps, while splash lubrication allowed oil to reach engine components through simple splashing rather than pressurized delivery systems. Each seemingly primitive choice served Ford's fundamental mission of creating engines that farmers could maintain indefinitely with basic tools. The low compression ratio prevented engine knock when running on poor quality gasoline, kerosene, or even corn whiskey, fuels that would destroy high-performance European engines. The flathead valve arrangement eliminated periodic valve adjustments that required trained mechanics, allowing farmers to operate their Model Ts for years without professional service. Thermosiphon cooling had no pumps to fail, no belts to replace, no complex components that might strand a farmer 50 miles from the nearest town. The splash lubrication system demonstrated Ford's engineering philosophy at its most radical. European manufacturers built engines with precisely calibrated oil pumps that delivered measured amounts of lubricant to each component. Ford's system simply let the crankshaft splash oil throughout the engine compartment, relying on gravity and centrifugal force to distribute lubrication. The method seemed crude, but it functioned even when oil levels dropped dangerously low, a common condition on farms where fresh oil cost more than many farmers earned in a week. Most revolutionary of all was Ford's tolerance philosophy. While European manufacturers machined engine components to tolerances of plus or minus 1/1000th of an inch, Ford deliberately specified plus or minus 10 thousandths, 10 times looser than accepted precision standards. Engineering purists visiting Highland Park expressed horror at tolerances they considered agricultural rather than automotive. Eugene Farkas understood the hidden genius behind Ford's imprecise specifications. When parts wore through normal use, they maintained proper function because the original tolerances accommodated significant dimensional changes. A farmer whose connecting rod bearing showed wear could remove the component, file the surfaces smooth with hand tools, and restore adequate clearances. The same procedure attempted on a precision German engine would destroy the component completely. The tolerance philosophy extended throughout the engine design. Piston rings sealed effectively despite loose cylinder bores because Ford's engineers calculated clearances that functioned across a wide range of dimensional variation. Valve seats accommodated wear by design, maintaining compression for decades of operation. Even the flywheel magneto-ignition system tolerated significant mechanical looseness while delivering reliable spark timing. Charles Ballou demonstrated the practical implications by assembling an engine using components selected randomly from production bins, parts manufactured on different days by different workers, using different machine settings, fit together without modification. The assembled engine started immediately and ran smoothly despite dimensional variations that would have prevented assembly of European precision engines. The manufacturing implications were profound. Ford's loose tolerances meant that production workers required minimal training to achieve acceptable quality. Machine operators didn't need to maintain precision settings throughout their shifts. Quality control inspectors could approve parts using simple go-no-go gauges rather than precision measuring instruments. Most importantly, production rates could increase dramatically because workers spent less time achieving unnecessary precision. By late February, the first vanadium steel engine blocks emerged from Highland Park's modified foundry. The castings showed exceptional strength characteristics, with metallurgical analysis confirming tensile strength of 170,000 pounds per square inch compared to 60,000 psi for conventional steel. The superior material properties allowed Ford's engineers to reduce wall thickness throughout the engine block, saving weight while increasing durability. Testing began immediately. Engineers subjected prototype engines to conditions that would destroy conventional power plants, continuous operation at maximum power, extended running without oil changes, operation on contaminated fuels, and thermal cycling between freezing temperatures and overheating conditions. The vanadium steel blocks survived punishment that cracked conventional cast iron engines, validating Ford's metallurgical gamble. The tolerance revolution proved equally successful in preliminary testing. Engines assembled with deliberately loose clearances demonstrated remarkable longevity as components wore to optimal dimensions during break-in periods. The wide tolerances that European engineers criticized as evidence of poor craftsmanship actually enabled superior durability by accommodating normal wear without performance degradation. As winter gave way to spring in 1913, Ford's radical engineering philosophy began generating measurable results. Engine assembly times decreased as workers found that loose tolerances made components easier to fit together. Quality reject rates dropped because acceptable dimensional ranges were wider. Most significantly, field reports from early Model T owners confirmed that Ford's crude engines delivered unprecedented reliability under conditions that disabled more sophisticated competitors. The engineering revolution was complete. Ford had proven that deliberate imprecision, unconventional materials, and simplified systems could deliver superior performance for real-world applications. The next challenge would be manufacturing these revolutionary engines fast enough to meet exploding demand for affordable, durable transportation. The experimental conveyor belt lurched into motion at 7:30 on the morning of April 1st, 1913, carrying the first flywheel magneto assembly in automotive history down a line of 29 workers stationed at precise intervals along the Highland Park factory floor. Each man had been trained to perform one specific operation, inserting a wire, tightening a screw, checking alignment, before passing the component to the next station. The mathematics of the experiment seemed impossible. Previously, one skilled worker assembled each complete flywheel magneto in 20 minutes, requiring intimate knowledge of electrical systems, mechanical tolerances, and assembly sequences. Ford's industrial engineers had decomposed this complex task into 29 simple operations, each requiring minimal skill but maximum repetition. The theoretical calculation suggested that specialized workers could produce one completed magneto every 13 minutes, a 35% improvement that would translate into revolutionary cost reductions across the entire manufacturing process. Charles Sorensen, Ford's production chief, walked alongside the moving belt with a stopwatch, timing each operation and adjusting the conveyor speed to eliminate bottlenecks. Worker number 7 consistently finished his wire insertion task several seconds before the next magneto arrived, creating idle time that reduced overall efficiency. Worker number 19 struggled to complete his screw tightening operation before the belt carried the component beyond his reach, creating a backup that threatened the entire sequence. The human dimension of the assembly line created challenges that no engineering calculation had anticipated. Workers accustomed to completing entire assemblies found the repetitive nature of single operations mind-numbing. Men who took pride in their comprehensive mechanical knowledge felt reduced to human automatons performing meaningless fragments of work. Several experienced assemblers requested transfers to other departments rather than endure the psychological tedium of endless repetition. Yet the system worked. By the end of April, the flywheel magneto line consistently produced components in 13 minutes compared to the previous 20-minute standard. More importantly, quality improved as workers developed exceptional skill at their specialized tasks. Worker number 12 could identify defective coil windings by touch alone. Worker number 23 detected misaligned armatures that would have escaped notice in traditional assembly methods. Ford's industrial engineers immediately began planning applications of moving assembly line principles to larger components. The transmission assembly process offered an ideal testing ground because it involved multiple sub-assemblies that could be fed into a main line from parallel feeder lines. By June, experimental transmission lines had reduced assembly time from 18 minutes to 9 minutes, a 50% improvement that enabled dramatic increases in daily production capacity. The breakthrough came in August when Ford's team implemented a complete chassis assembly line. The moving conveyor system transported bare chassis frames past 141 workstations, each staffed by workers performing specialized operations. Engine installation required 6 workers coordinating precise movements to lower the power plant into position and secure it with standardized bolts. Transmission mounting involved 4 specialists who aligned components and tightened connections to specified torque values. Body attachment utilized 12 workers operating in synchronized sequence to position, align, and fasten the passenger compartment. The results exceeded every prediction. Complete chassis assembly, which had previously required 12 hours and 28 minutes of skilled labor, now took 1 hour and 33 minutes, an 88% reduction in assembly time. Engine installation dropped from 594 minutes to 226 minutes. Transmission mounting fell from 18 minutes to 9 minutes. Final inspection and testing, once a 2-hour process, now required 37 minutes. These manufacturing improvements enabled Ford to slash Model T prices while maintaining profitability margins that funded continued expansion. The 1914 model year opened with a base price of $440, a reduction from $600 the previous year and less than half the $1,000 price from 1909. At $440, the Model T cost significantly less than comparable vehicles from any manufacturer worldwide while offering superior durability and simpler maintenance requirements. Orders flooded Highland Park faster than the expanded production capacity could accommodate. Dealers reported customers placing orders for vehicles that wouldn't be delivered for 6 months. Ford's sales department documented demand for over 300,000 Model Ts annually, production volumes that seemed impossible using traditional manufacturing methods, but achievable with assembly line efficiency. European manufacturers initially dismissed Ford's assembly line methods as American industrial vulgarity, unsuited to sophisticated automotive production. A prominent British automotive journal published an editorial declaring that mass production techniques may serve colonial markets adequately, but European customers demand individual craftsmanship that machine production cannot provide. German manufacturer Wilhelm Maybach visited Highland Park in September and pronounced the moving assembly line system mechanized barbarism that reduces skilled craftsmen to factory operatives. The criticism contained elements of validity that Ford's engineers acknowledged privately. Assembly line production created vehicles with less individual character than handcrafted European automobiles. Paint finishes showed slight variations between units. Interior appointments lacked the custom touches that wealthy customers expected from luxury manufacturers. Engine tuning reflected factory settings rather than individual optimization by master mechanics. But Ford's assembly line achieved something European craftsmanship could never match: consistent quality at revolutionary prices. Every Model T met identical specifications regardless of which worker assembled it or what day it rolled off the production line. Components were interchangeable between vehicles, enabling efficient repair operations anywhere in America. Most importantly, the assembly line made automobile ownership economically feasible for middle-class Americans who could never afford handcrafted European vehicles. French manufacturer Louis Renault warned that sacrificing precision for speed will ultimately destroy automotive quality standards throughout the industry. The prediction proved partially accurate as American manufacturers adopted assembly line methods that prioritized production volume over artisanal excellence. However, Renault failed to recognize that Ford's definition of quality differed fundamentally from European standards. While European manufacturers optimized engines for performance and refinement, Ford optimized for durability and maintainability under conditions that would disable luxury vehicles. By December 1913, Highland Park operated as the most efficient automotive manufacturing facility in the world. Daily production exceeded 1,000 completed vehicles, with annual capacity approaching 300,000 units. The moving assembly line had transformed automobile manufacturing from a craft-based industry serving wealthy elites into an industrial process capable of providing transportation for ordinary Americans. The revolution was complete, but its consequences were only beginning to emerge. Ford's assembly line methods would reshape not only automotive manufacturing but industrial production throughout America, creating the foundation for mass consumption that would define 20th century economic development. The dust-covered Model T wheezed to a stop in front of Highland Park's main engineering building on September 15th, its black paint obscured by layers of mud, sand, and road grime accumulated during 1,000 miles of deliberate abuse across Michigan's most punishing terrain. Test driver William Clay had spent 3 weeks subjecting the vehicle to conditions designed to expose every weakness in Ford's revolutionary engine design, fording streams that submerged the floorboards, climbing sand dunes that overheated conventional engines, and running on contaminated gasoline that would destroy precision European power plants. Chilled Harold Wills, Ford's chief engineer, approached the vehicle with the measured gait of a man who had witnessed too many engineering failures to celebrate prematurely. The engine compartment told a story of mechanical endurance that defied every prediction from Ford's competitors. Oil consumption totaled exactly 1 quart over 1,000 miles, a negligible amount that demonstrated exceptional sealing integrity despite the loose tolerances that European engineers considered barbaric. The vanadium steel engine block showed no visible signs of wear, with bore measurements indicating dimensional stability that exceeded specifications for new engines from competing manufacturers. Clay's logbook documented a litany of punishment that would have disabled any other automobile in America. The Model T had forded the Kalamazoo River 3 times, climbed the Sleeping Bear Dunes twice, and traversed logging roads in the Upper Peninsula that existed only as theoretical pathways between stands of virgin timber. The engine had run on everything from premium gasoline to kerosene purchased from rural general stores to corn whiskey obtained from a cooperative farmer near Grand Rapids. Temperature extremes ranged from pre-dawn frost that froze moisture on the radiator to midday heat that would have overheated water pump-cooled engines. Most significantly, the Model T had required 0 roadside repairs during its 1,000-mile ordeal. No broken parts, no seized components, no mechanical failures of any kind. The thermosiphon cooling system had prevented overheating despite extended operation at maximum power. The splash lubrication system had maintained adequate oil distribution even when the engine compartment accumulated dirt and debris that would have clogged precision oiling systems. The side valve engine design had functioned flawlessly on low-octane fuels that would have caused devastating pre-ignition in high-compression European engines. Wills removed the oil drain plug and examined the used lubricant flowing into a collection pan. The oil showed normal contamination from combustion byproducts, but no metal particles indicating abnormal wear. Compression testing revealed uniform cylinder pressures within 2% of factory specifications. Valve adjustment measurements showed no deterioration from the loose clearances that enabled field maintenance with basic tools. The endurance test vindicated every controversial engineering decision Ford's team had implemented over the past year. Wide manufacturing tolerances had accommodated thermal expansion and mechanical wear without performance degradation. Simple thermosiphon cooling had proved more reliable than complex water pump systems. The robust vanadium steel construction had withstood impacts and stresses that would have cracked conventional cast iron blocks. But the real proof arrived daily through Highland Park's mail department in letters from farmers, ranchers, and rural customers whose Model Ts were accumulating unprecedented mileage under conditions that destroyed other automobiles. A Nebraska wheat farmer reported 50,000 miles on his original engine, with maintenance limited to oil changes, spark plug cleaning, and occasional valve adjustments performed by the local blacksmith. His Model T had spent 4 harvest seasons pulling grain wagons, powering threshing equipment, and providing transportation across roads that existed only during dry weather. A Texas rancher documented even more demanding applications for his Model T, which served as the primary power source for his entire operation. The engine drove a lumber saw for fence post production, powered a grain mill for livestock feed, and operated an irrigation pump during drought conditions. Total accumulated hours of operation exceeded what most automobiles experienced in 50,000 miles of normal driving. Yet the engine continued running with original internal components showing minimal wear. Most compelling evidence came from repeat customers who purchased second and third Model Ts not because their original vehicles had failed, but because Ford's proven durability made them confident in the brand. A Montana cattle rancher ordered 4 additional Model Ts after his first vehicle completed 3 years of service hauling supplies across terrain that immobilized competitors' automobiles. A Minnesota logging contractor replaced his horse teams with Model T trucks after discovering that Ford's engines could operate reliably in sub-zero temperatures that prevented other gasoline engines from starting. However, engineering triumph created an unexpected crisis that threatened to destroy Ford's manufacturing revolution. By late 1913, Highland Park employed 13,600 workers operating the most sophisticated assembly line system in industrial history. Daily production exceeded 1,000 completed vehicles, but maintaining that output required a human workforce that was rapidly disintegrating under the psychological pressures of repetitive industrial labor. Employee turnover had reached 963% annually. Ford was hiring nearly 10 workers for every position just to maintain adequate staffing levels. The assembly line's mechanized pace and repetitive tasks created mind-numbing boredom that drove experienced workers to seek employment elsewhere, despite Ford's competitive wages. Men who had taken pride in their comprehensive mechanical skills found themselves reduced to performing single operations thousands of times daily without variation or intellectual challenge. Training costs consumed an increasing portion of Ford's operating budget as supervisors struggled to teach assembly line procedures to constantly rotating workforce. New workers required weeks to develop adequate speed and accuracy, during which their productivity remained below acceptable levels. Quality suffered as inexperienced employees made errors that experienced workers would have avoided. Most critically, the continuous training burden prevented supervisors from optimizing production processes that could have increased overall efficiency. Labor agitators recognized the vulnerability created by widespread worker dissatisfaction and began organizing strikes that could shut down the entire Highland Park operation. Union representatives distributed leaflets describing assembly line conditions as industrial slavery and demanding fundamental changes to Ford's production methods. The threat of coordinated work stoppages loomed over daily operations as worker grievances accumulated faster than management could address them. The automotive establishment watched Ford's labor crisis with undisguised satisfaction. Alexander Winton publicly predicted that Ford's dehumanizing production methods will ultimately collapse under the weight of their own mechanical ruthlessness. Charles Nash observed that no manufacturing system can survive when it treats workers as interchangeable machine components rather than skilled craftsmen deserving of respect. By December 1913, Ford confronted the supreme irony of his industrial revolution. His engineers had created engines capable of running 500,000 miles with minimal maintenance, but the manufacturing system required to build those engines was destroying itself through human attrition that no mechanical solution could address. The technical triumph meant nothing if Ford couldn't maintain a workforce capable of transforming revolutionary engineering into accessible transportation. The announcement that would transform American industrial relations forever came at precisely 10:15 on the morning of January 5, 1914, when Henry Ford stepped before a packed assembly of newspaper reporters in Highland Park's administrative building and delivered 4 words that stunned the business world: $5 a day. The figure represented more than wage policy. It constituted industrial revolution. In a single stroke, Ford had doubled the prevailing wage for automotive workers, creating immediate pandemonium among competitors who calculated that such labor costs would bankrupt any manufacturing operation within months. Headlines across America and Europe declared Ford either a visionary genius or a dangerous madman whose radical policies would destroy capitalist economics. The mathematics behind Ford's decision revealed the cold logic underlying his apparent generosity. Highland Park's accounting department had documented training costs of $50 per worker, while annual turnover rates of 963% meant that Ford was spending $6,800,000 yearly just to maintain adequate staffing. The $5 daily wage would cost approximately $3,200,000 annually, yielding net savings of $3,600,000 while eliminating the productivity losses associated with constantly rotating workforce. But Ford's true genius extended beyond mere cost accounting. Higher wages meant that Ford's own workers could afford to purchase the Model Ts they were building, creating a self-reinforcing economic cycle that expanded the domestic market for affordable automobiles. Every Ford employee earning $5 daily could realistically save for a $440 Model T, transforming assembly line workers from mere labor costs into potential customers. The announcement's immediate impact exceeded every prediction. Within hours of the wage increase becoming public knowledge, thousands of job seekers surrounded Highland Park's employment office, creating crowds so large that Detroit police were summoned to maintain order. Men arrived before dawn, hoping for positions that paid more than twice the prevailing industrial wage. Employment applications flooded in from across the Midwest as word spread that Ford was paying unprecedented compensation for factory work. Employee turnover disappeared overnight. Workers who had previously viewed assembly line positions as temporary employment now fought to maintain jobs that provided financial security unavailable anywhere else in American industry. The same repetitive tasks that had driven men to seek other employment became acceptable when accompanied by wages that enabled home ownership, family support, and genuine economic advancement. Productivity soared as experienced teams replaced constantly rotating novices. Assembly line operations that had required continuous supervision and frequent correction now functioned with precision that eliminated waste and maximized output. Workers developed exceptional skill at their specialized tasks, identifying quality problems before they could affect downstream operations and suggesting process improvements that increased overall efficiency. By April 1914, Highland Park achieved production rates that seemed impossible under traditional manufacturing methods. One completed Model T rolled off the assembly line every 93 minutes, an 88% improvement from the 12.5-hour hand assembly periods that had characterized automotive production just 2 years earlier. Daily output reached 1,000 vehicles, with annual capacity approaching 300,000 units. The production miracle enabled relentless price reductions that brought automobile ownership within reach of middle-class Americans for the first time in automotive history. Ford slashed the Model T's base price to $360, a 64% reduction from 1908 levels and less than half the cost of comparable vehicles from any competitor. At that price point, farmers, factory workers, and clerks could finance automobile purchases that would have been economically impossible just 5 years earlier. European automotive manufacturers watched Ford's success with mixture of admiration and horror. The $360 Model T undercut European luxury cars by margins that seemed to violate basic economic principles. How could American mass production achieve profitability at price levels that would bankrupt traditional craftsmanship-based manufacturers? The answer became dramatically apparent when World War I erupted across Europe in August 1914. Military forces on both sides discovered that Model T chassis could survive battlefield conditions that destroyed sophisticated European vehicles designed for smooth roads and professional maintenance. French armies acquired 11,000 Model T chassis and converted them into ambulances, supply trucks, and reconnaissance vehicles that functioned reliably under combat conditions. British forces deployed 20,000 to 30,000 Model Ts across European and African theaters, where the vehicle's simple construction and field-repairable design proved invaluable for military logistics. One American ambulance driver serving in France reported that our Fords could traverse shell-cratered terrain at 30 miles per hour when nothing else could move. The wide tolerances and robust construction that European engineers had criticized as primitive enabled superior performance under the most demanding conditions imaginable. Most convincing validation came from the engines themselves, which were beginning to demonstrate the 500,000-mile durability that Ford had promised. Model Ts manufactured in 1915 continued operating with original engines intact after accumulating mileage totals that exceeded the complete lifespan of most contemporary automobiles. Field reports documented vehicles surpassing 500,000 miles with minimal maintenance, proving that Ford's radical engineering philosophy had succeeded beyond even optimistic projections. The secret lay in Ford's controversial design decisions that prioritized longevity over performance. Wide manufacturing tolerances accommodated normal wear without functional degradation. Simple thermosiphon cooling eliminated water pump failures. Robust vanadium steel construction withstood decades of mechanical stress. Most importantly, the modular design enabled component replacement using basic tools available at any rural blacksmith shop. By 1916, Ford had achieved his ultimate vision: affordable, durable transportation that democratized automobile ownership while proving that American engineering ingenuity could surpass European craftsmanship traditions. The $5 day had transformed assembly line work from industrial drudgery into respectable employment that provided genuine economic opportunity for working-class families. The revolution was complete. Ford's combination of revolutionary engineering, innovative manufacturing, and progressive labor policies had created an integrated system that delivered unprecedented value to customers while generating sustainable profits for shareholders and meaningful wages for workers. The Model T represented more than successful automobile design. It embodied a comprehensive philosophy that prioritized utility over luxury, durability over sophistication, and accessibility over exclusivity. Yet within decades, American automotive manufacturers would abandon Ford's durability principles in favor of planned obsolescence that prioritized short-term profits over long-term customer value, creating the tragic irony of modern vehicles designed to fail at 150,000 miles in a world where 1913 Ford engines still operated after 500,000 miles of service.